Hi there, Physics 152. I'm Jason Harlow. I wanted to go through the activities for your second practical, which is happening this week. So this is all about electrostatics, which is exactly what Professor Kushner has been talking about. So the first activity is another numerical simulation, which when you click on, it takes you to this PHY152 Colorado site. Then you'll click on macro scale, and you see these little guys, and you can move them different distances from each other, and you can find the distances by looking at this ruler. The forces are listed there. You can also change the charge on the objects and play around with that. So there's a few questions to answer for that. That shouldn't take you more than 20 minutes. Activity 2 is the sticky tape experiment, where you're actually taping, getting some Scotch tape and taping it to a surface and then tearing it off. So for activity 2, part A, you're just taking a piece of tape and putting it on the table, and I recommend that you make a little loop handle so that you can, it's not sticky, so you can peel it back off again. You peel it off, and you do that a couple of times for multiple pieces of tape. For part B of this activity, it's a bit tricky. What you want to do is you're going to have two pieces of tape that you're going to separate. So you can read through the instructions carefully, but what I've asked you to do is put B on the bottom one, and then you take a second piece of tape and put it right on top of the first, kind of carefully. And of course, don't forget to make your little loop handle so that you can take these things. And then you can put T for this top one. T is on top of B. And then you take, both of them off. And then, once you've got these two pieces of tape, what you want to do is separate them. Okay? So now you have one called a T and one called a B. And you're going to do that a few times, at least 2 different times, and get several pieces of tape. It takes a lot of tape. And you need a comb that you're going to rub through the hair or fur of a mammal. So hopefully you have a mammal handy around. And lastly is the balloon experiment, which is estimated to be around 25 minutes, a little longer. But basically you're blowing up 2 balloons, tying them off, tying them each to a string that is about 1 meter long, and then rubbing them on your hair so that they repel one another. So these 2 balloons are attached to some high up surface, or something that you can hang something 1 meter off. And then you've got 2 balloons, so you take a balloon, blow it up. Now, I can never find string, but there's always shoelaces around, so I've actually just tied shoelaces to these balloons, which I worry about a little because the mass of the balloon might not be, like the mass of the string should be negligible compared to that of the balloon if we're going to do this analysis. But anyway, then what you do is you rub the balloon on your head a lot, and then take another one and rub it on your head a lot, so you get a lot of charge, about the same amount of charge on each. And when you hang them, they should repel one another because they're, well, as you'll see, should be equal charges repel. So, what I want to do in the remainder of this video is walk through an analysis of this for you so that you can figure out how you're going to estimate the charge on each balloon given this angle. Okay, so we have 2 strings which are attached to some fixed surface up above, and at the bottom we have 2 balloons which we will sort of treat as being point masses. And what's going on is both of these strings are hanging at some angle theta away from the vertical, and there is a distance r between the centers of those 2 balloons. So what will happen is there will be an electric force, repulsive force, between the 2 balloons, Fe, which will be Coulomb's constant, times, they'll both be, by the way, This will be negative Q, charged up to negative Q, and this will be charged up to negative Q. So they're Q squared, assuming that when you rub a balloon on your head, it picks up a negative charge, and they've both picked up the same amount of negative charge divided by r squared. So let's draw the free body diagram for the right balloon. What's that going to look like? Well, there's the balloon. You have upward here is the tension, which is totally unknown. You have in the negative y direction is mg, the gravity force, and then you have the repulsive force from the other balloon, which we've already calculated is F sub e. And this tension force is at an angle theta. So the way I would do this is I would balance. This is static equilibrium. And so if you set up your y-axis to be up and down, your x-axis to be back and left to right, if you balance the y forces, then all the forces pulling upwards equal all the forces pulling downwards. So I would say T, tension, times cosine of theta is equal to mg. And if you balance the x forces, everything pulling to the right minus everything pulling to the left should be equal, then I would say T sine theta is equal to F sub e, which is equal to this k q squared over r squared. And you can just, I guess, divide by the sine theta and the cos theta. You set the tension equals the tension. So this means that the tension is mg over cos theta, and this means that the tension is equal to k q squared over r squared sine theta. So setting to eliminating tension here, you've got mg divided by cos theta is equal to k times q squared divided by r squared sine theta. And we're going to solve for q because that's what we're trying to get here. Trying to estimate how much charge I put on a balloon when I rub it on my head in coulombs. So solving around for q, what do I get? I've got m times g times r squared times sine theta divided by Coulomb's constant times cosine theta is equal to q squared. So in the end, I've got q is equal to the square root of m times g times r squared times tan theta, because sine over cos equals tan, divided by Coulomb's constant. So that's the equation that you can use. So just to sum up, you've got g, you're going to measure r, the distance between those balloons when they're in static equilibrium. You're going to measure theta, so the amount of angle that they're kind of hanging outwards from vertical. You know k Coulomb's constant. The other thing you need to know is what is the mass of a balloon. So that's actually not entirely obvious. I actually have this whole mixed party balloons bag, which says that it has 100 balloons in it. And what I did is I went on the scale and I measured my mass, when I wasn't holding the balloons, and then I went back on the scale and measured my mass when I was holding the balloons. And I found that my mass went up by 0.4 kilograms when I was holding 100 balloons. So each balloon that's in here, it's not got air in it, I guess, each empty balloon should have a mass of 0.4 kilograms divided by 100, which is roughly 4 grams. So, and I think that's probably the least accurate thing, and it neglects totally the mass of the shoelace as well. But I suggest that you use 4 plus or minus 1 gram to be the mass of the balloon, unless you can think of a better way of measuring the mass of your balloon. So I think that's it for today's video, and good luck with your week, and I'll see you next week.